Hello, everyone. It's a great pleasure to speak here, and I will talk about optimized photonics. Photonics has many applications of interest today, as all of you know, some of which are outlined here, ranging from optical interconnects for data centers, optical neural networks, LIDAR for self-driving cars, biosensors, imaging system, quantum technologies, augmented reality systems. But all of these applications actually require miniaturization of optics. They require highly efficient and densely integrated photonic chips. And free space optic solutions would not be really feasible for many of these applications because you cannot simply fit the resulting circuit into a footprint of, for example, augmented reality glasses. So the question is whether we can enable all of that, and whether in photonics we can go through the same revolution that we went through in electronics in 20th century, where from computers that occupied the whole building in 1950s, today we have much more powerful computers inside of our mobile devices. So let's revisit the state of the art of photonics today and see if this is possible. State of the art photonics, unfortunately, is not yet at the level which would enable such a level of integration that is necessary. It is pretty bulky. We have tens of micrometers per component. It is very sensitive to environment, fabrication errors, temperature errors, and so on, which is why people have to incorporate post-tuning elements such as heaters and electrical control, which further complicate circuits. Also, photonics is designed by manual parameter tuning of only a few design parameters, which leads to suboptimal solutions and also limited functionalities, and often lacking functionalities for a lot of interesting applications. And finally, state-of-the-art photonics is often inefficient. For example, even in commercial systems, we have in-coupling losses that are greater than 50%, which may be okay for some applications if you have sufficient amount of power, but in some cases is far from what is needed for operational system. And also, in many cases, because of such tremendous losses and needs for tuning and elements and so on, we end up with systems that do not really perform better than electronic systems. For example, energy consumption could be on the order comparable to electronics circuits for interconnect systems. So how do we do better than that? How do we make photonics that is truly competitive and it would work much better than electronics for many applications? And this is the question that my group has been looking into for a very long time, about 15 years. The checklist of goals that we would like to achieve is given here. We would like to achieve better device performance than what we know today, compact footprints, robustness to fabrication and environmental errors, new functionalities, and could we eliminate brute force design and manual parameter tuning from the design process so that you don't even have to be an expert in order to design a good photonic circuit. And we believe the answer to all of these questions is yes. We were able to develop approach that can optimize photonic devices in 3 dimensions, which is necessary for achieving all of these functionalities. And we've been working on improving this approach for the past decade or so. And if you're interested in learning more about this field, which we refer to as inverse design in photonics, you can read this review article that we wrote together with a group of Alejandro Rodriguez from Princeton recently, which will give you an overview of all of the interesting directions where people are thinking about applying photonic optimizations. So what are we actually doing? Let me start from a very simple example of a waveguide band and explain you how optimization in photonics can dramatically impact the system's behavior. If you are interested in building a waveguide band and you don't really know much about optics, you may naively try to do it just by taking a waveguide and simply bending it at a 90 degrees angle. And that would produce some kind of bending of light, but it would not be very efficient. You would lose most of the power at the corner and it would have efficiency of only 26%. Then if you know a little bit more about photonics, you can say, well, instead of doing this, I will basically just curve it a little bit at the corner and that should work better. And indeed, this should work better and you will be able to bend light with about 83% efficiency. But again, as you see from this movie, you are still losing quite a lot, 70% of the input power at that corner. So how do you do better than that? Well, as all of you in photonics know, you can actually band it with a larger radius, and that should work even better. And indeed, you can make it pretty much almost 100% efficient, but the radius of banding will be very large, and that would occupy a very, very large footprint of your circuit. And that's not something that you would like to do, because you will need a lot of real estate just to make a simple waveguide band. But it is nevertheless very efficient. So how do you then band light in a small footprint, right? Something like a couple of micrometers of a footprint at most, with a very high efficiency? Can you get 100% efficiency while having a small footprint? Manually, people can try to solve this problem, and people have addressed it in configurations such as photonic crystal bands and so on. But this was all with the brute force optimization, which was extremely painful and time consuming. Instead of doing that, you can apply inverse design. And let's say you would like to band light with high efficiency, meaning you maximize transmission from the input to the output waveguide, and you have this unknown structure at the corner that you need to optimize in order to do that. So how do you do that? You define a figure of merit. You try to change permittivity inside of this corner, which has 2 microns by 2 microns footprint, until you can maximize transmission, achieve nearly 100% efficiency. And you do that by running a lot of different electromagnetic simulations, and you're tweaking these pixels and permittivity of these pixels in the process. But there is a problem. I mean, if you pixelate it to 40 by 40 nanometer pixels, you will still have 2,500 degrees of freedom, because you have 50 by 50 pixels in this corner, which means that you have 2 to the power of 2,500 possible designs. And this has to be designed in 3 dimensions, which means that you have to run this many electromagnetic simulations. And if you're very lucky, you will end up with a good solution at some point in the process, but most likely you will not be able to do that during your lifetime. So how do you search through this enormous parameter space in a smarter way so that you can actually solve this problem? And what we do is basically gradient-based optimization. Parameter space is really complex. You still need to search through it, but instead of just randomly picking, flipping these pixels, you are actually flipping them in guided way, guided by the physics of the problem. So you start from some structure, you calculate gradients based on whatever figure of merit of your problem is, and those gradients tell you how to update the structure so that you improve the behavior as you're traveling through the parameter space. Calculation of gradients can be very time consuming. So in order to speed that process up, you're using adjoint optimization, which allows you to calculate gradients from 2 electromagnetic simulations, forward and backward simulation. You still calculate gradients, but only from 2 electromagnetic simulations, which is much faster, and then use calculated gradients to update the structure. And if you do all of that, you can actually solve this problem very fast. Something like this could be solved in an hour on in 3 dimensions on GPUs, gaming GPUs, not supercomputers. Here is how the optimization process looks like in the movie you saw on the left, and the final structure would have a very high efficiency, transmission efficiency, nearly 100% in a very small band. Not something that you could intuitively come up with, although for this problem it kind of makes sense that it would look something like this. It has some reflectors that help it bend in the corner. So that was a waveguide band. Of course, we solved many other problems in the process. For example, problem of mode converter. So I'll actually flip here through a few problems and give you an idea how the optimization process looks like. So here is a mode converter, for example, that should convert first to second order mode inside of a very small footprint, about 2 by 1 micron footprint. This is orders of magnitude smaller than any adiabatic mode converters that people would typically use to solve this problem with high efficiency. So many orders of magnitude smaller than state of the art. Again, if you just pixelate it, even to a large pixels, 100 by 100 nanometers, you have too many degrees of freedom. You will not really be able to manually flip pixels and go through this 10 to the power 112 different solutions until you find the right one. So you cannot really do blind search for this problem. But instead, you do optimization, you do gradient descent by following the figure of merit of the problem. And here is how that optimization would look like. Here is the first stage where you allow permittivity to vary continuously. You use this to initialize the second stage. And in the second stage, you basically binarize permittivity so that you obtain something that you can fabricate. And on the right, you see electromagnetic field solution, and this is basically telling you that you are converting into the right mode at the output. And keep in mind that efficiency of the problem is a part of the figure of merit. So you don't stop until you reach the target efficiency, which here is 90%. This full optimization takes about 400 iterations. Each iteration has 2 electromagnetic simulations. We run this in 3 dimensions so that you obtain something that is real, and full optimization takes about an hour on gaming GPUs. And that could be improved and sped up further by using some of the methods that I will mention to you later on. So it's a very, very efficient, but it also requires development of fast electromagnetic solvers. Here is another problem that we typically face in photonics, which is the design of a wavelength splitter, WDM device. Let's say you would like to split 1.3 from 1.5 microns in a small footprint, something on the order of 2.8 by 2.8 microns, again in 3 dimensions. And you define figure of merit for each of the channels. You incorporate fabrication constraints into the process so that you end up with something that you can fabricate. And here you can see how the design process looks like. And as you're designing this structure, you're traveling through this enormous parameter space. These pixels are changing according to the gradients that you are calculating until you end up with a solution that satisfies your requirements and your figure of merit. So you see they're still changing, but you're ending up eventually with something that is fully fabricable. It has only 2 different colors in the plot, black being silicon and white being air that you need to etch out of silicon on insulator. And once you make something like this, it would look like this. This is another solution in the same parameter space. So this is the etched pattern in silicon on insulator, 2.8 by 2.8 microns. And on top right corner, you see the structure that you actually designed for this wavelength splitter. Here are other views of the same structure hooked up to waveguides. And here is the same structure with superimposed fields at 1.3 and 1.5 microns. And if you look at how structure behaves as you are scanning the wavelength at the input, first 100 nanometers will be transmitted to the top port, and the second range of wavelengths around 1.5 microns will be transmitted to the bottom port. So highly non-intuitive solution, but ends up being very robust to errors in fabrication, temperature, and splits very broad bands around these 2 wavelengths as desired. So now, just to summarize, you can use inverse design to design a variety of devices. You just define figure of merit, you define what function you would like to have, how you would like to map inputs to outputs, or whatever else you have as a figure of merit. And you can incorporate fabrication constraint, and that way you can build structures that are robust and insensitive to errors. And when you implement these wavelength splitters, like 2-channel wavelength splitter that I was showing you before, or 3-channel wavelength splitter that is shown underneath in also very small footprint, 4 by 5 microns, and measure these devices, they will all perform the same, although you don't really have any tuning elements that you would typically have inside of your photonic structures that would complicate its performance. So on top here, you have transmission characteristics for many different 2-channel wavelength splitters that are measured, and at the bottom, you have transmission characteristics for many 3-channel wavelength splitters that are measured. And they all line up on top of each other, although we didn't do any post-tuning. So that is the beauty of inverse design. And if you're interested in learning more about what we actually do in order to design devices, you can read this review article that we wrote recently in Applied Physics Review. If you're interested in using our software Spins is available for licensing from Stanford Office of Technology Licensing. Many companies, university groups, or government labs are using it. It's called SPINS, Stanford Photonics Inverse Design Software. We have also released the basic version of that software on GitHub in open source. It's called SPINS-B. That's the basic version. It doesn't really have fabrication constraints. It doesn't have graphic interfaces. It's not really fully loaded as the commercial version, but a lot of academic researchers are playing with that one as well. And it's available on GitHub at this link. So that's the story of SPINS development and inverse design. But of course, if you would like to use any of these design devices in practical systems, designs have to be compatible with high throughput fabrication, which is why we spent the last several years trying to make sure that they are compatible with Foundry-based fabrication. We are happy to report that they are fully compatible with Foundry-based fabrication. So what we do in that case is we take design rules from a particular foundry, and we incorporate them into the design process so that all the devices that we design using our inverse design software would basically follow those design rules. So when we send the layout to a foundry, they would fabricate something that they can fabricate, and then we just receive fabricated devices and we can measure them afterwards. So here I'll show you results from our collaboration with John Bowers from UC Santa Barbara, and devices were fabricated in AIM Photonics, but we've been collaborating with several other foundries throughout the world. So we sent a variety of devices, some of which we had demonstrated previously and some of the new ones. We wanted to compare some of the already demonstrated devices with our university-based fabrication, and also wanted to see the behavior for some of the designed ones that we had never fabricated. And here I'll just show you some of the results that we achieved that are really promising. Here is an example of a 3-channel wavelength demultiplexer that I showed you previously. One of the devices that we had previously made by electron beam lithography and in our university fabrication facility. Here is the same device that fabricated in AIM Photonics, exactly the same design. Here is the theoretically predicted behavior, and here are the measured results. And these are actually measured results for many devices on the same chip without any post-tuning. So quite remarkable and quite exciting. Here is another device that we had not previously demonstrated, a spatial mode splitter converter. This is the device that splits and converts first and second order mode. First order mode would be routed to top left port. Second order mode is converted to first order mode and routed to the bottom left port. We sent this layout, actually cascade of these two devices, and then we measured cascade of these two devices after they were fabricated in photonics. And here is the theoretically predicted behavior for the cascade of two devices. And here is the measured result for the cascade of two devices. So actually excellent fit between the two. Keep in mind that this is the superimposed loss for two devices, so it's only 1.5 dB per device. Theoretically, it was predicted to have a loss of about 1 dB, and the small discrepancy between the measured result and the theoretical prediction is because we designed it for minimum features of 80 nanometers, and minimum features in the foundry that they could reliably fabricate were around 90 to 100 nanometers. And again, this is in 220 nanometers silicon on insulator. So that's very promising, very exciting, and tells you that you can actually make large circuits by using this high throughput fabrication. Of course, there are many different elements that you can optimize and design. You can design, for example, a variety of grating couplers. You can improve traditional grating couplers. You can build broadband grating couplers, not something that we already have in our library of known traditional photonic devices. You can also build, implement wavelength demultiplexing grating couplers. You couple two colors and you split them into two different channels. Also very important in simplifies circuits and make them more compact. Or you can make grating couplers for a variety of other materials that are more fabrication constraints, such as diamonds, shown here, as I'll describe to you in a moment. And apart from these particular types of devices, you can also develop other functionalities, including dispersion engineering, which is a very important problem to solve in nonlinear optics or in beam steering, in LIDAR problems. But of course, manually doing dispersion engineering is extremely difficult, and you can never really draw this desired behavior, omega versus k relation, and hit that by brute forcing the problem. People have spent decades trying to build slow light structures with high efficiency, desired dispersion in photonic crystals. They could never really draw dispersion and achieve exactly that. They can maybe do it in a narrow wavelength range, but not in the broader wavelength range, or not with the desired group index. If you rely on the optimization techniques, you can exactly do that. You can draw desired dispersion, whatever is physically possible, and you can optimize the structure within fabrication constraints that exactly hits that desired dispersion. So for example, here in this broader wavelength range, we can have a group index of 25. We can also engineer micro-resonator dispersion. Here we start from traditional racetrack resonator. Without degrading Q factor, we insert an element that controls the dispersion of a microresonator, so that if you are using, for example, this system for microcombs, you will have flat dispersion and you will obtain a better frequency comb. So those are very important and unsolved problems in photonics and nonlinear optics that you can solve by using optimization. So apart from the problems that I was already describing that people had been working on previously, there are also new functionalities that you can achieve. And now I'd like to spend a few minutes showing you our results that were of new functionalities, new photonics functionalities that were completely enabled by using these optimization approaches. The first problem that I'd like to briefly discuss is non-reciprocal transmission and routing in passive silicon photonics. You all know that an isolator, on-chip isolator, is a very important area of research for photonics, but usually solutions either require large structures that have to be controlled precisely, or some introduction of some exotic materials on the chip, which complicates manufacturing dramatically and typically leads to structures that also have large losses. We wanted to come up with a simple solution that would enable some specific set of applications, for example, range measurements in a LIDAR, without the need to develop these complicated isolators. And we were inspired by the theoretical work of Andrea Aldu from City University of New York. His team has proposed this non-reciprocal transmission in structures that consist of a cascade of two resonators, Lorentzian and Fano resonators with intrinsic nonlinearity. If you couple different amount of power in the forward and backward direction into your nonlinear resonator, what would happen is that transmission characteristics would shift by a different amount, and therefore, the laser frequency in the forward and backward direction, you will have different transmission. So you observe non-reciprocal behavior. And Andrea's team has demonstrated, this in microwave circuits, but a demonstration in optical regime was missing. Had been missing because it had been very difficult to design all of these elements with the desired transmission characteristics. That was, in fact, very difficult to do it by hand. But of course, you can actually instead do this by using optimization tools. You start from system of two resonators, and then you optimize coupling regions until you receive the desired transmission characteristics. And this is what we're doing here. And you can see movies of how these coupling elements are designed so that you can achieve both Fano resonant transmission and Lorentzian resonance. And once you achieve the desired block and layout of the desired block, you can fabricate the whole structure. Here they are. You can measure transmission. And as you can see, transmission matches the theoretically predicted behavior exactly. And of course, all of this is done in 3 dimensions by incorporating fabrication constraints into the process. And once you make the whole system, you can measure its behavior. Here in the dynamic power range, where this behaves as an isolator, non-reciprocal element, you're transmitting forward pulses and you're blocking backward pulses. This is experimental result. In the yellow, these yellow slots, you are supposed to receive backward pulses, but they're blocked. When isolation is off, when you're outside of the dynamic power range, you are not blocking backward pulses. And you can perform this at 10 gigahertz rate. You see you have forward signal, but no backward signal. And that's excellent. You can do it with high speed. And keep in mind that this doesn't require any exotic materials. It's just a small piece of silicon, several tens of microns of silicon, without any electrical control, without any exotic materials. Why would you use something like this? Well, in LIDAR systems, for example, you have to do optical ranging measurements, which means that you have to send pulses to the target, reflect them, and then send them to a detector. And based on the delay between the forward and backward pulses, you're performing ranging measurements. This ranging measurement requires routing of the backward reflected pulses into detectors. And of course, you can do that with a variety of switches that people are developing. But all of these switches are either limited by insertion loss, or have extremely large footprint, or have very large power usage, or they're slow. As opposed to our device that I just demonstrated that has extremely small footprint. It's fully passive, so no loss. It has very small insertion loss, smaller than the others, and also has extremely large switching time. It's tens of gigahertz of speed. So if you take this element, which is just basically a block of silicon, and use it in ranging measurements, we've done ranging measurements for distances of up to 60 meters. So you can basically just add an extra element into your silicon photonic circuit without the need to build a full isolator, perform ranging measurements in a LIDAR. Very inexpensive, very simple, just add extra block into whatever you're sending to a foundry. Then another interesting demonstration of new functionality that I'd like to emphasize is on-chip integrated laser-driven particle accelerator. All of you are familiar with accelerators. Accelerators are relying on RF or microwave fields inside of very, very long accelerator facilities to accelerate charged particles. And of course, each stage of acceleration has very complicated microwave and RF circuits in order to achieve that. And since circuits are also very large and each stage is very large, you need miles of accelerator in order to get to interesting energies for either medical imaging or material science, or especially high energy physics, modern high energy physics experiments. So we wanted to miniaturize accelerators. And of course, electromagnetic fields are scalable. If you just shrink wavelength of light, you can shrink, in principle, shrink accelerator. So thinking about just going from microwaves to optical fields, you have a 10,000-fold reduction in the wavelength. So if you use the IR infrared fields in order to perform acceleration, you should be able to shrink the accelerator by 10,000 times. So you could basically go from something like a few miles of an accelerator to a wafer. But of course, that's not straightforward, because you cannot really simply shrink microwave components and then operate at optical frequencies. You have to redesign everything, and you have to do it using the electrics. But that's not available off the shelf, which means that this is a new problem that you have to solve. And we've been working for the past 5 years on the 8-chip accelerator on chip project, which is led by Bob Bayer from Stanford and Peter Pommelhoff from Erlanger. And I will show you our designs, inverse designs of accelerator stages, and our demonstrations of acceleration gradient inside of these stages that are only 30 micrometers long and made in silicon. And using infrared laser field that is coupled to this structure, which is fully scalable, we were able to achieve gradients that are completely comparable to state-of-the-art RF accelerators, 30 mega electron volts per meter. Since you're achieving this only in a 30 micrometer accelerator stage, that means that you can cascade hundreds or thousands of these without problem on a silicon wafer and build basically accelerator that would reach energies that are interesting for a lot of state-of-the-art experiments and applications. So here is how the accelerator stage looks like. You have a grating to couple laser, you have a waveguide, you have your vacuum waveguide, right? So this is a waveguide for propagating laser field. This is a vacuum waveguide for where you couple your electrons. This pattern here is optimized in such a way that electrons is always in phase with the field inside of this structure. Of course, you have to take into account the speed with which electron arrives here, which for us is 83 kilo electron volts of energy. These are electrons coming from modified scanning electron microscope. Here is how the field pattern would look like inside of the structure. Electrons would go through this vacuum channel. If you don't turn on the laser, you just look at the electrons that propagate through the structure. They would exit this stage with the same energy, 83 kilo electron volts. So that's the blue curve. And then if you turn on the laser, which is coupled here, produce the pattern here that would accelerate electrons, and they would exit with increased energy. And acceleration gradient, as I mentioned, is 30 mega electron volts per meter. This is, of course, just one stage, 30 micrometers long. So if you cascade hundreds or thousands of those, you can start with these electrons from scanning electron microscope and go to mega electron volts. And you can already use these electrons for a lot of practical applications in medical imaging, in radiation, and so on. And you'll have it all done inside of a wafer, silicon wafer, a few inches of a silicon wafer. So that's very exciting and interesting. But everything that I showed you so far was pretty much done in silicon. So some of you may think that there is something special about silicon and its connection to optimization and inverse design. There is nothing special. Inverse design is applicable to any materials that you would like to work with. In fact, now I will show you some of my team's work on other materials, such as diamond, shown here, or silicon carbide. In fact, inverse design is completely agnostic in terms of the material. All you need to know are material properties, refractive index. You also need to know constraints of your fabrication process because, of course, fabricating diamond is much harder than fabricating silicon. So if you are designing diamond devices, you will have very different fabrication constraints than when you're designing your silicon devices. So that's what we're doing. And here you see some inverse design diamond devices with superimposed field patterns that were fabricated by my team at Stanford using a process that was pioneered by Paul Barkley at Calgary, which is basically three-dimensional carving of diamond structures. Does this impact behavior of the structures? Well, in fact, this inverse design would dramatically impact behavior of these diamond devices. And in particular, these are devices that we develop for applications in quantum technologies where you care about efficiencies even more, right? And fabrication is more challenging. You cannot really map traditional devices. These are suspended structures and so on. So what we would typically do in the past when we're doing experiments with some color centers, quantum emitters in diamond, is we would make these notches at the input and output and then couple light in and out of notches. But this has very low efficiency, something like 1 or 2%. So then you have to wait something like 10 seconds integrate transmission, and after 10 seconds you start barely seeing some sort of feature in transmission spectrum that is a feature of your cavity resonance. But that's of course not scalable because it takes a very long time to even see a blip in the spectrum that you attribute to the cavity resonance. Instead of that, in the same footprint, you can optimize these grating couplers. They're optimized with our fabrication constraints for diamond, which is 100 nanometers minimum feature size. They're fully suspended, and this already has efficiency of about 30%. So after 1 second of integration, you see a beautiful peak that is clearly a cavity resonance. So you can achieve much larger enhancement in counts, reduction in experimental time, and this is clearly enabling you scaling to multiple nodes. And we're actively working on that, in particular in terms of scaling to more complicated circuits or incorporating quantum emitters, as is important for a variety of applications. So here is another circuit where you couple light from your coupler. You go to something like a beam splitter, split into two resonators, recombine, and then go to another coupler and measure behavior of this system, showing that you can also tune everything on resonance with each other. And something like this could be used to, in principle, entangle two quantum emitters that are sitting inside of these two resonators. Another material that we worked with actively is silicon carbide, right? And I will now spend some time telling you about our work on this material, of course, combined with optimization. But before I do that, I'd like to spend a minute highlighting some of the very important properties of silicon carbide, which may be actually ideal photonics material. Silicon carbide has very strong optical nonlinearity. It has also second-order optical nonlinearity as opposed to silicon. And its second-order optical nonlinearity is only a factor of 3 weaker than for lithium niobate. But as you'll see in a moment, it's a much easier material to process, and you have much higher quality photonics than in lithium niobate. So you make up for that difference very easily with higher quality of photonics. It's a piezoelectric material. It has excellent thermal conductivity and large band gap. It is silicon compatible, no cross-contamination. It's available on wafer scale. People routinely use it to make electronic circuits. I mean, silicon carbide is a material that is used for high-power electronics, and you can buy 6-inch wafers. And it hosts high-quality quantum emitters, some of the best quantum emitters, qubits for quantum technologies. There is no other material out there that provides all of this. Silicon is a great photonics material. Boom in photonics started about 20 years ago when silicon on insulator was commercialized, right? And that was about 40 years after commercializing bulk silicon. But of course, silicon doesn't have second-order optical nonlinearity, no known high-quality optical interface quantum emitters, and you actually can't really achieve everything that you can achieve in lithium niobate as shown here. And band gap, of course, is not as large. Lithium niobate, there has been a lot of activity on lithium niobate for the past 10 years, and that was triggered by commercialization of thin film lithium niobate on insulator in 2010. That was about 20 years after bulk lithium niobate wafers are commercialized. Of course, lithium niobate is a very interesting nonlinear optics material, but it's very hard material to process and achieve high quality photonics. And you can't make electronics in lithium niobate, and there are no really high quality quantum emitters that are known as of now. So it's not really offering everything that you have in silicon carbide. Silicon carbide, bulk silicon carbide wafers were commercialized in 1990s. They're quite inexpensive. You can get 6-inch wafers from companies like CLEO. But as of last year, there was no commercial thin film silicon carbide on insulator, which is why we had to develop it ourselves. So how do we do this? We spent a couple of years working on smart cut, which is what people use for silicon on insulator. But that didn't really work very well for us because we are interested in embedding quantum emitters in those structures. And smart cut relies on ion implantation of the structure, ion bombardment of the structure. So you end up introducing unintentional defects inside of your structure that would basically degrade the quality of your quantum emitters and also quality of interfaces in optical structures. So instead of that, what we do is we wafer bond silicon carbide on oxidized insulator and then grind structure, polish it, and do RAE tinning. And we end up with few by few millimeters of a uniform silicon carbide, thin film silicon carbide film on insulator. This is not a limit to how large you can do. If you had a better facility than what we have at Stanford, you could also make larger chips. But few by few millimeters is plenty of real estate to make very complex photonic circuits, which is what we're doing. We can also do very high quality photonics. These are some of our silicon carbide circuits. On the right, you have silicon carbide on insulator. This is suspended. You can undercut material underneath if you are interested in doing something for quantum and achieving removing all of the oxide from the interface with silicon carbide. But we measure quality factors that are greater than 1.1 million. And that's basically comparable to silicon quality factors for the resonators with dimensions of about 20 micrometers. So here is a Q of 1.1 million that was measured here. We measure it in transmission through Waveguide. And here you see some optimized inverse design grating couplers ending at that waveguide. So this optimization process is fully compatible with silicon carbide fabrication, which is not the case for lithium niobate yet because fabrication process is more difficult. We are also using it for nonlinear optics. I mentioned that silicon carbide is excellent nonlinear optical material. It has third order nonlinearity, but also it has a really good second order nonlinearity. In the first measurements of second harmonic generation, where we converted 1.5 micron pump to 750 nanometer second harmonic, we measured waveguide to waveguide efficiency of 360% per watt, which is already respectable. But since then, we've improved Q factors of resonances by a factor of 10 or more, which means that this number should now be updated to something like 36,000% per watt, right? So 36% per milliwatt, and could be much better than that. So you have really state-of-the-art nonlinear optics. And we've recently also demonstrated optical parametric oscillation in silicon carbide and microcombs. Here are our results of showing optical parametric oscillation with 8 milliwatts of threshold. And you see also occurrence of a microcomb. So we're working on improving this further and making useful devices for metrology and sensing. I have mentioned that silicon carbide is also a very exciting material for quantum optics because it hosts quantum emitters, interesting quantum emitters. My team has primarily been working with silicon vacancies in silicon carbide, which are just missing, in 4H silicon carbide, which are just missing silicon atoms. That's your artificial atom. And when you couple those quantum emitters to resonators in this silicon carbide on insulator that we developed, we can actually achieve very good coupling, excellent photonic interface, and enhancement of emission by a factor greater than 100 without any degradation in the emitter properties, because we end up with pristine silicon carbide films on insulator. Same is the case for diamond. I'm just using this picture to show that you can couple color centers inside of diamond structures with optimized couplers and optimized interfaces. In this case, the color center that we used in the experiment is thin vacancy color center in diamond. So it's missing 2 carbon atoms and an extra thin atom in between. And we measure properties of these color centers in diamond structures, inverse design diamond structures, and they have the same line width and the same properties as these color centers in bulk pretty much, which is quite exciting and quite promising. So these optimization methods, inverse design, and fabrication methods are fully compatible with all of these even novel fabrication techniques and quantum emitters. So from here, we do plan to make larger circuits. You will never really have perfect systems. You always have to deal with inhomogeneities, imperfections, that not all of the emitters will have equal properties or be where you want them to be. But that's the case in all of different systems, superconducting qubits or atomic systems, where people also need extra knobs to tune, such as optical tweezers or rewiring circuits or so on. In photonics, we can certainly do that. We can add another layer, for example, of silicon nitride photonics on top of silicon carbide to rewire the circuit accordingly. And then you can also do quantum frequency conversion to map all of these quantum emitters to your fiber optic network. So that's what we're planning to do. But I'd also like to give you kind of my vision for what is coming next in optimized photonics. Before I do that, let me kind of briefly summarize what I've been talking about, right? So we started with traditional designs, but those traditional designs in photonics or state-of-the-art photonics have many drawbacks in terms of the footprints. So they are suboptimal, they are not energy efficient, and they're designed by brute force searches. So you cannot really achieve functionalities that are desired, and you actually have low efficiencies. And in many cases, you beat the purpose of even using photonics in your applications. And then inverse design, you know, that we talked about, you can design devices for a particular functionality and with high efficiency, small footprint. But then there are some drawbacks, right? Everything that I showed you so far has a relatively small footprint, up to about 10 by 10 microns in 3 dimensions. So what is the problem? Well, the problem is computational bottleneck. If you look at how much time it would take you to run a single electromagnetic simulation as a function of the simulation volume, this is what you would see. And this is what we benchmark for GPU-based finite difference frequency domain method, and that's the method that my group uses during the optimization, right? So that's clearly prohibitive in terms of designing larger structures, because when you go to simulation volumes that are larger than 100 cubic wavelengths, you will basically have the simulations that you would explode. You can still optimize devices, but you will need something like 2 hours per optimization step, and then 400 iterations would bring you to 2 days of optimization, and that's not what you want to do. So designing some active devices for nonlinear optics or metasurface optics that are very large structures would be beyond the timeline, beyond the reach of the current optimization tools. You could do it, but you would actually, it would take you a really long time, so it would not really be very practical. So how do you solve that problem? Well, you have to accelerate your electromagnetic simulations. One thing that we did in collaboration with our friends at Google were data-driven approaches to simulation acceleration. You can accelerate electromagnetic simulations by keeping in mind that during inverse design, you're basically in your iterative steps performing simulations of correlated devices. So you can learn something from that and then accelerate future simulations. And indeed, this is what we did for a variety of devices. And we have shown that our data-driven approaches perform much better than traditional simulation methods and preconditioners for solving matrices, and that in fact, you can actually speed up the simulation time by a factor of 10 or more. So that's one thing that we do, you know, learning something about the simulations that we're performing in order to speed them up. But what about scaling size even further, right? For example, how do we optimize the full metasurface and not just one simple building block of a metasurface? And metasurfaces can be millimeters in size. And often when people design only a single element of a metasurface, they neglect interaction between these unit cells and elements, which leads to non-ideal behavior of the whole metasurface. So what we would like to do is to design the whole thing at once, millimeters of metasurface at once for a particular target. To do that, we cannot really use traditional electromagnetic solvers because they would take extremely long time to simulate, to run each simulation. And you know that you have to run 2 simulations per optimization step. So running thousands of simulations in series is prohibitive. But you have to come up with new methods for metasurface simulations. And we have come up with a method called transition matrix method, where basically you look into a linear transformation that this system of scatterers applies on incident field. And based on that, we can perform electromagnetic simulations of metasurfaces much, much faster. So if you compare actually our electromagnetic solver to commercial finite difference time domain solvers, such as Numerical, for simulation of 60 by 60 micrometer metasurface, you can do much, much better on a single GPU. Here is a simulation time for Numerical, which kind of explodes after a few tens of microns. And here is our simulation time for T-matrix method, which is orders of magnitude faster. And with this, basically, you can simulate the whole, optimize the whole metasurface in a reasonable amount of time, right? So that's what we're working on right now. And we're already running some preliminary optimizations. So with that, I'd like to wrap up my talk and say, give you the main message that I wanted to give, that photonics optimization is critical for implementation of scalable and practical systems. If you're interested in using our software, SPINS, Stanford Photonics Inverse Design Software, you can license it out from Stanford Office of Technology Licensing. Many companies are using it. Also government labs and academic groups can license it as well. We also have open source version on GitHub. This is the basic version, not fully loaded, but you can also play with it. It's on this link. And of course, we published many papers on what we do. So if you would like to learn more about the background of what we're doing, here is one of our recent references, review papers in applied physics reviews. But of course, there are a lot of problems that we're trying to solve. And this is a work in progress, and we're making it faster and more scalable and coming up with new features. As those of you who are following SPINS and SPINS-B know, there are always new releases coming up. So right now, integrated circuits, photonic integrated circuits, state-of-the-art photonic integrated circuits would look something like this, with a lot of tuning elements and identical blocks. But we think that in the future, they may look quite different, but they'll be more compact, more energy efficient, more robust, and more practical. And with that, I'd like to thank our sponsors and our collaborators, and also my research group at Stanford, people who did this work. And I'd like to thank you all for your attention. Thank you.